Okay, so in this case, now because we know the displacement here, and now we want to calculate the velocity and acceleration of the of this harmonic motion. So we will just differentiate this with respect to time. So when we differentiate one time, we will get displacement, and the second time we will get the velocity. So x dot, which is velocity, will be a um, omega cos omega tau here, or omega t, and then x double dot is again equal to a, which is acceleration, and this is a omega square, and sine, but it will be negative omega t here. And now we also know that the cos can be changed to sine if you want to make it equivalent to this equation here. So it will become a, or omega a, and then sine omega t plus pi by 2, and then this will become equal to omega square a sine omega t plus pi here. So this means that the we can also write the displacement and acceleration in this form here. So thus the velocity and acceleration are also harmonic with the same frequency of oscillation, but lead the displacement by pi by 2, which is 90 degrees, and 2 pi radians. So this is pi radians. So pi radians, respectively. Now, as you can see, if you plot the displacement as we did earlier, so this is how the displacement look like. So at x equal to 0, which is if t is equal to 0, it's x is equal to 0. So if you just put t equals 0 here, you will get x equals 0, and then it's is a sine function here. Now the x dot, which is this function here, which is cosine function or sine function pi by 2. So if you plot this with respect to time, so you will get this plot here. And similarly, if you plot x double dot, which is acceleration, you will get a plot which is again a sine function, but where it's arranged is a bit different. So it's you are multiplying this with a negative sign. And again, you can see here that the velocity is leading the displacement by 90 degrees, and then acceleration is again then leading the displacement by 90 degrees, or leading the displacement by 180 degrees. So if you just plot that this is your x here, so x is omega t here, the angle, and then the velocity here, which is this line here, is at angle of 90 degrees to the displacement, and then acceleration, which is this line here, is at 180 degrees to the displacement here. Okay, now again, we know that the acceleration here, which is x double dot, was omega square a sine omega t plus pi here. So again, as you can see here, that this is our acceleration here, or we can also write the acceleration, which was minus omega square a sine omega t, and we know that this a x was equal to a sine omega t here. This means that we can represent this x is equal to a sine omega t. So if we just replace this a sine omega t here, so x double dot will become equal to minus omega square x. So we get this equation here. So now, so in simple harmonic motion, acceleration is proportional to the displacement and is directed toward the origin. This means that the acceleration is directly proportional to the displacement, and the negative sign mean that it's always uh, uh, toward the origin here. Okay, so we just derived these equations. So this was the displacement equation, this was the velocity equation, and this was the equation for the acceleration here. And we then plot these values here. And again, you need to see here that the amplitude here is a, because it's a sine omega t. This is t here, and then here the amplitude here is omega a here, and then the amplitude here is omega square a. Okay, so now we can talk about uh, the undamped free vibration. So in this case, when a spring mounted body is disturbed from its equilibrium position, its ensuing motion in the absence of any imposed external force is termed as free vibration. So this is what we call is the free vibration, because there is no external force here. You are just move the this mass from its equilibrium position, and then just will leave it, and then it will vibrate by its own. So there is no external force that will vibrate this system here. And in every actual case of free vibration, there exists some retarding or damping force which tend to diminish the motion. So it can be, for example, a friction between the mass and the surface here, or it can be air resistance. Um, so common damping forces are those due to mechanical and fluid friction here. So we will first consider the ideal case where there is no damping. So the damping forces are small enough to be neglected. And then in the next lecture, we will also consider the damping forces. And now for this specific case, you can draw the free body diagram if you displace this from its equilibrium position. So the mass is m, so the weight will be mg. The normal force will be in this direction here. So the normal force and mg will cancel each other, and you have the uh, you have this spring force, which will be in the opposite direction to the x here. And now if we consider this horizontal vibration of a simple frictionless spring mass system, as you can see here. So note that the variable x denote the displacement of the mass from the equilibrium position, which from this system is also the position of zero spring deflection. And if you consider this figure here, so figures show that a plot of the force, which is the spring force, necessary to deflect the spring versus the corresponding spring deflection for three type of springs. So we discussed this earlier in the previous lectures. You can have a linear spring. So if you increase the x, the spring force will increase. And then you can have the soft spring. So if you increase the x, this is how the spring force will change. And you can also have this hard spring relationship. But in this case, we will just consider this red line here, which is the linear spring. So the relation between the spring force and the displacement will be Fs equal to Kx here. And now such a spring exert a restoring force minus Kx on the mass. That is when the mass is displaced to the right. The spring force is to the left, and vice versa. Now here the constant of proportionality, which is this K, is called is the spring constant. You can also call it modulus or the stiffness, and this has the unit of Newton per meter here. We discussed this earlier. So thus the equation of motion for the body is obtained by first drawing the free body diagram, as you already we did it here. This is the free body diagram, and now we want to write the equation of motion here. So you will use the Newton's second law, which is summation of all the forces in x direction equal to max, because the body is accelerating in the x direction, and we will assume that acceleration is positive in this direction here. So x double dot is our acceleration, so we will call that mx double dot, and we will assume that this is our positive direction here. So then the spring force is in the negative direction, so it will be minus kx and mx double dot here. So this is the equation of motion for this specific case, which is undamped. So there is no damping here, and there is no external force here. So it is just the spring force, which is internal force. Um, so this is the undamped free vibration because no external force and no damping here. So note that the acceleration is proportional to the block displacement, and which is simple harmonic motion. So in the simple harmonic motion, we derive the equation that the acceleration should be directly proportional to the displacement, which is also in this case here. This is also a simple harmonic motion. And now if we rearrange these terms, uh, so if you just try to simplify this equation, so if you say that mx double dot plus kx equals 0, so if you just move this kx to this side here, or you can say that x double dot plus k divided by m x equals 0, or you can say that this will become equal to x double dot plus omega n square x equals 0. So this omega n here is is what we call uh, is the natural frequency, and the unit of this omega n is radian per second here. So omega n is because this omega n square, so this is square here. So omega n square is k divided by m. So if you want to calculate the natural frequency, so which will become k divided by m under the root. So the natural frequency is just k divided by m under the root. This means that if you know the stiffness and the mass, you can calculate the natural frequency, and the units here will be radian per second. Okay, now you can also consider in this case the mass was on this surface here, and it was vibrating in this direction. You can also have another situation that the mass is hanging from this direction here, from here, and it's just hanging. So if there's no mass here, so this will be the original position of the spring here. But if you attach mass here, so there will be some deflection of the spring, and we call this deflection is static deflection here. So now consider a block suspended, and when the place into motion, oscillation will take place. It natural frequency, which is omega n, and this omega n is the property of a system, so it depends on the k and m of the system here. And in this case, the deformation of the spring in the static equilibrium position. So this is our static equilibrium position because the spring and mass is just stationary here. And if you just let it to be there, so it will stay there, and this is their equilibrium position. Okay, so the deformation of the spring in the static equilibrium position is delta. So this is uh, the uh, the static equilibrium position deformation, and the spring force, which is and you can draw the free body diagram. So this will be the spring force for the static equilibrium position, and the weight will be in the downward direction here. So in this case, you can again apply the summation of all the forces uh, in this direction, in y direction, is equal to my double dot here. Or you can call this even x, so you can say that it will be your mx double dot. But again, we know that here the body is stationary, so this thing will be equal to 0. So this means that summation of all the forces in y direction equal to 0. So this means that this k delta minus w equals 0, or you can say this that k delta is equal to mg. So at this static equilibrium position, the k delta is equal to mg. So if you want to calculate this static deflection, which is the deflection at static equilibrium position, you can calculate it from this equation here. But now we want to give this system some vibration. So what we will do, we will displace this from this static equilibrium position, and this delta is already the deflection here, and you give it a deflection x from this position here. So now the total deflection here will be delta plus x. So by measuring the displacement x from the static equilibrium position, the forces acting on M are K delta plus x. So now the total force is acting on the system is K delta plus x. And you have x dot, and x double dot is the acceleration and velocity. We are assuming that it's positive in the downward direction here. So now we can derive the equation of motion for this system here. So again, we will say that summation of all the forces in x direction equal to mx double dot. And again, here we are assuming that this is our positive direction here. So as you can see on this system here, we have weight here, we have this spring force here, and so if you write the equation of motion here, so uh, you have k, and then you have delta plus x here, which is the negative, and then you have plus mg, which is positive because we are taking downward direction is positive because acceleration is in the downward direction, so we are taking the downward is positive. You have this equation here, so you can plus minus kx plus mg is equal to mx double dot. But again, now you can see from the static equilibrium position, and we derived this equation earlier, that k delta is equal to w. So if k delta is equal to w, which is mg, this means that this term and this term will cancel each other. And from this system, what we will get minus kx is equal mx double dot. And you can simplify this equation here. So which will become mx double dot plus kx equals 0. Or you can say that it will become x double dot plus k divided by mx equals 0. Or x double dot plus omega n square x equals 0. And now this is exactly the same equation that we derived for the system when it was vibrating horizontally, and this system is now vibrating vertically, and the mass can also have effect here. But we saw that at this equilibrium position, because these two forces are equal to each other, which you can cancel here, so then the final equation is exactly the same as the previous equation here. So then you don't need to worry about if the system is vibrating vertically or the system is vibrating horizontally. In both cases, the equation of motion is exactly the same. Okay, so now this is the equation of motion here. So this is the second order homogeneous linear differential equation. So this equation is second order because we have x double dot, and this is homogeneous equation because the right hand side is 0, and this is linear equation because this omega n is not a function of x here. So then you know that we know from the mathematics, that is from the differential equations, that for this specific system we have the solution which look like this. So a sine omega nt plus b cos omega nt. So if you have this equation and you want to find its solution, so we want to find the equation for x here. So x will look like this. So this is the equation for the x here, and now we want to calculate here this a and b, which are obviously the unknown, uh, uh, and a and b represent two constant of integration here. So now we want to calculate these a and b, but now we also want to calculate the velocity and acceleration, which you can again determine by differentiating this equation with respect to time here. So we will become x dot, which become a omega n cos omega nt minus b uh, sine omega n sine omega nt. And you have a here, so which will be x double dot, and this will become a omega n square sine omega nt and minus b omega n square cos omega nt. These are the equation for the velocity and acceleration now. Now the integration constant, which is a and b, if you want to calculate, so you calculate these uh, by using the initial condition for the problem. So the initial condition we have for this case is that if you suppose that the block has been displaced a distance x1 to the right from its equilibrium position, and given an initial positive velocity v1 directed to the right. So if this is our initial condition, that at time equals 0, x is equal to x1 and v is equal to v1. Okay, so now these are the equations and these are the initial conditions. So now we want to put the initial condition in these equations and we want to calculate a and b here. So if you put the first initial condition, that is t is equal to 0, x is equal to x1. So what you will get, b equal to 0, sorry, b equal to x1. And if you put the second initial condition here, which is that t is equal to 0, v is equal to v1. So if you, then a will become equal to v1 divided by omega n. So if you just put time equal to 0 here, so for the first case, as you can see that okay, so for the first case, which is this case here, so if you put x is equal to so x1 will become equal to a, and this will be 0 plus b. And for the second case, will have to put it here. So v1 will become equal to, because this is sine cos 0, so a omega n and minus 0 here. So from here you will calculate a here, which will be v1 divided by omega n. So now this means that the x become equal to so x become equal to v1 divided by omega n sine omega nt and plus x1 cos omega nt here. And now we know that this equation may be expressed in terms of a simple sinusoidal equation. We have this equation here, and we can now also represent this in a different form. So if you just say that c cos pi and b is equal to c sine pi here. So if instead of a and b we use this thing here, then the x will become equal to c cos pi sine omega nt and plus c sine pi cos omega nt here. And this equation, we know that x can be written as c and sine omega nt plus pi here. So from here we can also write x in term of c and pi, which this is another way to express this equation here. Now, because this is a bit complicated equation, consists of sine and cosine, but this is simple equation which is just have only one sine function here.